This video is an overview of orbital mechanics from a historical perspective and is 3.2.1 from our curriculum. So our big concept for this lesson is that the study of orbiting bodies dates back at least to ancient Greece. Early efforts to explain how orbits worked centered on observations of the planets in our solar system. In this lesson, you will gain an appreciation for these early orbital mechanics pioneers. So first, let's just do a little review. Let's start with what an orbit is. An orbit refers to the motion of one body around another. Although not always the case, one object is typically very large in relation to the other. In this case, the smaller object is said to orbit around the larger, and the larger is typically presumed to be fixed in space. Now let's review what a satellite is. Today, we typically think of a satellite as something human-made that orbits the Earth. While this is true, anything that orbits another body is technically referred to as a satellite. The planets in our solar systems are all satellites of the Sun, and the Moon is also a satellite of the Earth. So let's go way back in time to some of the original studies of orbital mechanics in ancient Greece. So ancient Greeks were interested in orbital motion, and so they began to study this, specifically Aristotle, who studied the motion of the planets in the night sky. And he was able to gain a general understanding at the time that Earth was fixed in space and that the heavenly bodies moved around it. Now today we know that is not true, but that was the original hypothesis. So let's move forward in time and take a look at Copernicus. So Nicholas Copernicus lived from 1473 to 1543, and he was the first to theorize that the Earth and other planets actually revolved around the Sun, and he assumed that the motion was circular. So he took accurate measurements and found that his assumption was not completely accurate, and his theory was actually incredibly heretical at the time and went against the teachings of the church. So now we're going to move on to Brahi. So Tycho Brahe lived from 1546 to 1601, and he was a lecturer at the University of Copenhagen and is actually responsible for gathering a wealth of accurate planetary motion measurements. So he had a really fantastic telescope and was able to document a lot of the planetary measurements that we did not have before that time. And then there is Kepler. Johannes Kepler lived from 1571 to 1630, and he was an assistant to Brahe. And he actually is the first to propose that planetary orbits were elliptical, which we do now know to be true, and proposed that laws of orbital motion that are still used today. So because of his research and deciding that the orbits were elliptical, we actually are able to accurately measure orbital motion. And then we have Robert Hooke, who lived from 1635 to 1703, and he was a member of the Royal Society, and he debated Newton on facts about orbital mechanics. He and Newton were colleagues and peers that debated orbital mechanics frequently. And then of course we have Newton. Isaac Newton lived from 1643 to 1727. He grew interested in mathematics from reading about astronomy, and from Kepler's work where he deduced the existence of an inverse square law of attractive force, and then proposed a theory of universal gravitation. He wrote Principia, which is considered the greatest scientific book ever written, which also posits his 3 laws that we use in class all the time. So in conclusion, the interest in orbital motion dates back to ancient history. The first formal assertion that the Earth was not the center of all things was around the mid-16th century. And the study of orbital motion led directly to Newton's Principia and the 3 laws that we consistently use in physics and aerospace engineering and a lot of other fields today. And then the study of orbital motion from the 16th century until Newton focused on how the planet orbited the Sun. And then Newton proposed why the planetary orbits exhibit the behavior they do with the theory of universal gravitation. And then Kepler's and Newton's laws govern our understanding of orbital mechanics still today.